Okay, let's try some of the hardest problems that we're going to do in one-dimensional motion. And they are about when two things collide or when two things meet. The important thing to remember for these, we're not going to learn any new equations. We're just going to apply equations we already know in a specific situation. The important thing to remember is if two things are meeting, that means they're in the same location, which means that their final displacement of whatever object A is equal to the final displacement of whatever object B is. Now we also know from our third equation before that final displacement is equal to initial plus v naught t plus 1/2 at squared. And because we know that if this equals this and this equals that, then that equals that as well. So we can replace the final displacement with what final displacement equals for both objects. So we can say initial displacement of A plus the initial velocity of A times time, and time is the same for A and B because the time scale doesn't change, plus 1/2 the acceleration of A times t squared. And that is equal to the initial displacement of B plus the initial velocity of B times t plus 1/2 the acceleration of B t squared. And we just replace A and B with whatever our two objects are. So when you write what you know, you need to make a column for object 1 and for object 2 to help keep you from being confused. So let's try this example. A mouse is running at a constant velocity of 3.2 meters per second. So we have object A is going to be the mouse. It doesn't really matter. It's just the first one. And our cat is going to be object B. So the mouse is running at a constant velocity. That gives us information before we even get to the number. We know the acceleration of our mouse is 0. And his velocity, his final velocity and his initial velocity, is 3.2 meters per second. The cat starts 4 meters behind the mouse. So a lot of physics is about visualization. We have our mouse here, and I'm a terrible artist, so I'm just going to use letters. And here's our cat. And this is a distance of 4 meters. And they're all running this way to the right. So you can put whatever measurement scale you want on here. Your cat can be at 0, and your mouse can be at 4. Your mouse can be at 0, and your cat can be at -4. Your cat could be at 10, and your mouse could be at 6. It doesn't matter as long as the distance is 4. And if we're going to say that this direction is positive, that it's in the correct in terms of direction. So it's either, 4 or less as we go from mouse to cat. So I'm going to go with this value because the more zeros we have, the easier it gets. So this is the only situation where your initial displacements won't always be 0. So cat's initial displacement is 0 and mouse's is 4. And again, you can use any one of these setups that you want. As long as you're consistent, the math will still come out right. So he starts out 4 meters behind the mouse and runs at a constant velocity. So we know the acceleration of our cat is 0. Guess I should put my A's and B's on. So, of 5.3 meters per second. So our velocity and our initial velocity is equal to 5.3 meters per second. And if you look at this and you think logically, they're both running in the same direction because they both have positive velocities. So it makes sense the cat has to be running faster, otherwise he's never going to catch that mouse. So the question asks you, how long does it take? It's asking you to solve for t, and how far, the final displacement. Regardless of what you are asked for in a where do two things collide problem, the first thing you always have to find is time, because it's the only thing that applies to both. So if we look at this equation up here, we know everything in it except for time. So we're going to plug into it. And if you don't understand how we derived this equation, please talk to me about it, because it's important to understand the logic behind our steps and not just be able to repeat them because you saw them. In order to be truly successful in physics, you need to understand the logic, the why did we do this, not just be able to repeat it. So if we plug in, we've got 4 meters, and we know that our velocity never changes, so it's 3.2. Time. We know that acceleration is 0. The cat starts out at 0. So if we simplify this and get rid of some of the zeros, and if it bugs you to have the units in there, just drop them and put it in at the end, okay? I don't want you to get messed up just because of units. So you can see that this is, if you ignore units, this is 53 or 5.3 t, and this is 3.2 t. So we're going to combine like terms by subtracting 3.2 t from both sides. So 5.3 minus 3.2. And this is where people make most of their mistakes, is they get all the way to here and then they don't do the algebra correctly. So if that's you, just ignore this, and now it's just 3.2 t. And you can see that you need to combine your like terms. So we get 4 meters equals 2.1 meters per second t. And now we divide both sides by 2.1. And you get a time. Let's talk about significant figures. I miswrote this here because it is 4.0. So we have 2, 2, and 2. We round to 1.9 seconds. So it takes less than 2 seconds for that cat to catch the mouse. Now we need to know where. How far does the mouse travel? And to do this, we need to go back and use just this equation before you combine it. And we need to talk about just one of them, because theoretically they're in the same place. So you could plug into that equation using either all the A information or all the B information, and you should get the same answer. Now, depending on significant figures, it might be off slightly. If we kept 7 significant figures and we had measurements that exact, then the answers would be very much the same. But because we've got 2 significant figures here, if you plugged in for the cat, you might get a slightly different answer than if you plug in for the mouse. I'm going to plug in for the cat for the sole reason that it has 2 zeros instead of 1, and that makes the math easier to do. So x equals x naught plus v naught t is 1/2 at squared. And again, if you do the mouse, your answer might be slightly different, but I understand that, and I take that into consideration, so don't worry. So 0 is 5.3 times 1.9 plus 0. And we still should have two significant figures, so they should meet at about 10 meters. And so you can write that like this, the decimal, or you can write 1.0 times 10 to the 1 meters. Okay, let's do another practice. In a mating display, a black goat and a brown goat run at each other to butt their horns. So we know that we're going to have the black goat. It's going to be my A, and it's arbitrary. You can pick whichever one you want. And the brown goat is my B. And they start from rest 6.75 meters apart. So there's my black goat and my brown goat. This is the positive direction. And I'm going to say this is 0 and this is 6.75. I know it's silly, but I suggest making a little sketch like this that will help you visualize it and help make sure that you're being consistent about your directions. So the initial displacement for our black goat is 0, and for our brown goat is 6.75 meters. And if they start from rest, that means the initial velocity is 0. Because of the complexity of the math involved in a when and where two things collide problem, either the initial velocity is going to be 0 or the acceleration is going to be 0. That keeps the math from becoming above the heads of some students taking this class. So the black goat accelerates at a rate of 0.745 meters per second squared, and the brown goat accelerates at a rate of 1.204 meters per second squared. Where and when do they meet? Now let's look at our sketch here, because our black goat is going to accelerate this way in the positive direction. But his acceleration is less than the brown goat's. So if the brown goat is running this way, they're never going to meet. But they're running towards each other, run at each other. That means the brown goat is traveling towards 0, right? And that means the brown goat is traveling in the negative direction. That is the number one mistake made in a problem where two things are running towards each other. Make sure that if they're going towards each other, one is moving in the positive direction and one is moving in the negative. So now we can plug into our equation, and the derived one we used last time, in order to find out when they meet. So because we know these are 0, we know that we don't even have to really consider that variable. And we know that this is also 0. So 0 plus 1/2 run out of space there. So. And I'll simplify it a little bit. do the 1/2s. When you get negative, don't forget. And if it helps, ignore the units. And you can see you've got a number t squared and a number t squared. So we're going to combine like terms. So I'm going to add this to both sides. And we know that's meters per second squared. I'll write it down there. Now to get t squared by itself, we're going to divide both sides by our 0.9745. And we get that t squared equals 6.9266 and some more. And that would be second squared. And then we're going to take the square root of that. And get that they're going to meet at 2.6318 seconds. Let's talk about significant figures. We've got 3, 4, and 3, so we're going to round this to have 2, or 3 significant figures. 0.63 seconds before they meet. And we can come up with where by using that second equation. I'm going to talk about the black goat because it has an extra 0, which simplifies the work I have to do. And again, if you use the brown goat, you might get a slightly different answer. Do not worry, show your work, and I understand that they're not always going to be perfectly the same. And when you do your math, we're still going to have 3 significant figures. You get that they meet at 2.58 meters. So they meet about here. Please do some practice problems and ask me for help if you need them. When you're working on the assignments where you have to do these, if you have questions, please ask me. I am always happy to help you check your work or make sure you're on the right path before you submit it even. If you aren't sure, you can list what you know and send me that in an email and say, Miss H, is this right? And I'll check it for you before you finish the problem. Just ask for help if you need it.